A student carries out 2 experiments in the laboratory based on succinic acid, butane dioic acid, CH2COOH brackets 2. Part A. Aqueous succinic acid can be neutralized by aqueous sodium hydroxide, NaOH. This reaction can be used to determine a value for the enthalpy change of neutralization. The student follows this method. Add 50.0 centimeters cubed of 0.400 moles per decimeter cubed succinic acid to a polystyrene cup. Measure out 50.0 centimeters cubed of 1.00 moles per decimeter cubed of NaOH, which is in excess. Measure the temperature of both solutions. Add the NaOH to the aqueous succinic acid in the polystyrene cup. Stir the mixture and record the maximum temperature. Calculate a value for the enthalpy change of neutralization in kilojoules per mole. Assume that the density of all solutions and the specific heat capacity C of the reaction mixture are the same as for water. Firstly, we need to highlight the key pieces of information in this question. Our first key piece is that we've got 2 moles of H2O, or a 2 molar fraction. And that's important because the enthalpy change of neutralization is the energy released when forming 1 mole of H2O, and we've got 2, so that means our final answer will have to divide by 2. Our next key piece of information is our volume and concentration of succinic acid. We're going to use these to work out the moles of succinic acid. Then we need to look at our temperature readings because we will be using temperature change. So as I've said, our first action that we're going to do is we're going to work out the moles of succinic acid. We do this using an equation triangle of NV times C, which means we're going to take volume and multiply this by concentration to get the number of moles of succinic acid. So that would be 50 times 10 to the negative 3 because we're converting centimeters cubed into decimeters cubed, and then multiplied by 0.4, which gives us 0.02 moles of succinic acid. Next, we're going to use Q equals mc delta T. If we label this equation with the information we already know, well, m is mass, and that will be the total volume because we're told that the density of all solutions is the same as water. So 1 centimeters cubed equals 1 gram. And the total volume is 100 centimeters cubed, so our total mass would be 100 grams. C is specific heat capacity. Again, we're told it's the same as for water, so in our data sheets we're told that it's 4.18. Delta T is the temperature change which we can calculate, would be 26.5 minus 21.5, which gives us 5 degrees Celsius. This means that Q would be Q equals 100 times 4.18 times 5, which then equals, in joules, 2090 joules. But we want kilojoules per mole. So converting this to kilojoules, we would get 2.090 kilojoules. Then we can work out kilojoules per mole because we've already calculated moles, and this would be 2.090 divided by 0.02, which gives us plus minus 104.5 kilojoules per mole. But the very first thing I said was that we need to divide our answer by 2 because we have 2 water molecules produced. So it would be 104.5 divided by 2, which equals 52.3. And we need a negative sign in front of our 52.3 because the enthalpy change of neutralization is negative. To get the 4 marks for this question, you get your first mark for working out the number of moles of succinic acid, 0.02. Your second mark for working out Q, or 2090 joules. Your third mark for working out 104.5 and that this is positive or negative at this stage. And then your fourth mark for working out that you need to divide this by 2 because there are 2 water molecules produced, and writing minus 52.3 on the answer line. Part B. Succinic acid is esterified by ethanol, C2H5OH, in the presence of an acid catalyst to form an equilibrium mixture. The equilibrium constant Kc for this equilibrium can be calculated using the amounts in moles of the components in the equilibrium mixture, using expression 5.1. A student carries out an experiment to determine the value of Kc for this equilibrium. The student mixes together 0.0500 moles of succinic acid and 0.150 moles of ethanol with a small amount of an acid catalyst. The mixture is allowed to reach equilibrium. The student determines that 0.0200 moles of succinic acid are present in the equilibrium mixture. Part 1. Which technique could be used to determine the equilibrium amount of succinic acid? So the answer to B part 1 is titration, and writing titration on the answer line would get us our mark for this part of the question. Part 2 says that we need to write the equation for the equilibrium reaction that takes place. For this part of the question, we need to look at our expression for Kc, and Kc is written as products over reactants, and the power that it's raised to shows us the stoichiometry of the equation. So, using this information, we can work out the equilibrium reaction that takes place and write this. So, our reactants would be brackets CH2COOH brackets 2 plus 2, because it's raised to the power of 2, C2H5OH, and then we need an equilibrium arrow, and then we would produce brackets CH2COOC2H5 brackets 2 and 2H2O. To get the mark for this question, you need to have the full complete equilibrium reaction. Part 3. Draw the skeletal formula of the ester present in the equilibrium mixture. The ester they're asking us to draw is here, which I've just highlighted. If we start by drawing our first ester link, because this is a repeating ester, we would have our oxygen bonded to a carbon, which is then doubly bonded to an oxygen. Our first ester link will be connected to our C2H5, which would be 2 peaks of skeletal formula. Then we mirror what we've drawn on the left with our C doubly bonded to an oxygen and then bonded to another oxygen. But this ester has a side chain, it has our CH2, so we need to account for this in our skeletal formula. So at the ends, we need to draw another peak showing another carbon in this ester. To get the mark for this question, you need to have the full, complete, correct ester drawn. Part 4. Kc is the equilibrium constant in terms of equilibrium concentrations. Why can expression 5.1 be used to calculate Kc for this equilibrium? The reason why expression 5.1 can be used is that the volumes cancel. Alternatively, you could say that there are the same number of moles of products and reactants, or the same number of moles on both sides of the equation, so they're going to cancel as well. To get the mark for this question, you need to either say that the volumes cancel, or that there are the same number of moles on each side of the equation, or the same number of moles of products and reactants. The reason why this is the answer for question 4, or the reason why there are the same number of moles of products and reactants, we can tell this from the Kc expression, or expression 5.1. And so we can see that we've got on the numerator something raised to the power of 1 and something raised to the power of 2. And on the denominator, we've got something raised to the power of 1 and something raised to the power of 2. So that means that the stoichiometry of the equation, we're going to have a 1, 2 on the reactants and a 1, 2 on the products as well. And so that means that there's going to be the same number of moles of products and reactants based on the stoichiometry. Part 5. Calculate the value of Kc for this reaction. Show your working. In this question, we're going to firstly highlight the key pieces of information, and that would be any reference to moles, because we're going to use the number of moles left in the equilibrium mixture to work out the value of Kc. And that's because we're going to use a method called ICE in this video. So firstly, using this method, we need to write our reactants, CH2COOH brackets 2, C2H5OH, and our products. So that would be CH2COO C2H5 brackets 2 and H2O. We then use the information in the question. I stands for initial number of moles, and our products initially would have 0, so we can fill this in the table. We're told that initially we have 0.05 moles of succinic acid and 0.15 moles of ethanol in our mixture. We then need to work out the change. We do this using the equilibrium value of moles of succinic acid that we're given, and we're told that it's 0.02. So that means we have a change of negative 0.03, and we can apply this change to anything with the same stoichiometry. So for our products, we would have the opposite change but the same value. So it'd be plus 0.03, making the number of moles present at equilibrium 0.03 for our ester. For water and ethanol, or H2O, and C2H5OH, we have double the number of moles. So our change would be doubly as big. So that'd be 0.06 or minus 0.06 for ethanol and plus 0.06 for water. So we know the water moles at equilibrium, and the ethanol moles at equilibrium would be 0.15 minus 0.06, which gives us 0.09 moles of ethanol in the equilibrium mixture. So now we're going to plug in the numbers that we've just calculated for the number of moles in the equilibrium mixture. We're going to use our expression for Kc and plug in the moles. So that would be 0.03 times 0.06 to the power of 2. We're applying the same powers of 2 as we're given in the expression for Kc, and we would divide by 0.02 times by 0.09 to the power of 2. That gives us a value for Kc of 0.67, which we will then write on the answer line for this question. To get the marks for this question, you get your first mark for correctly calculating the number of moles in the equilibrium mixture for your products, so the ester and water. You get your second mark for working out the number of moles in equilibrium for ethanol, or 0.09 moles, and your third mark for correctly substituting the number of moles you've calculated in the equilibrium mixture into your expression for Kc, and finding that it's 0.67.